that said, if we get into some of the, a little bit of electrical math coming up and I get something completely wrong, please let me know. I'm learning, same as everybody when it comes to hobbies. So anyways, I'm here to talk about Raspberry Pi and Arduinos. Quick poll, how many people here have a Raspberry Pi or have used one? So yeah, a fair amount of people. What about Arduinos? Less. Couple, though. Okay. Today I'm going to cover basic introduction to Raspberry Pi and Arduino. I'll go over some basic lingo, so if I start throwing around some fancy words, you might understand what I'm talking about. And do a quick electronics primer. We'll do a deeper look into Raspberry Pi along with some programming examples, and then same thing with Arduino and some programming examples there as well. And at the end, I've got 2 Pis online right now and 2 Arduinos that I can plug in and do some live demos on as well. So, introduction to Arduino and Raspberry Pi. Let's define what they are. I'm going to define them as small programmable computers with air quotes, because an Arduino really isn't a full computer. But Raspberry Pis and Arduinos have something very special about them called general purpose input and output pins. These allow you to interact with your world. They allow you to sense the world and to control things as well. And that's one of the major draws for a Raspberry Pi or an Arduino. They're also cheap. Raspberry Pis run $35 at the most. Depending on what Arduino you buy, you can get all the way down from $10 to up to $50 for an Arduino. So it's a very low barrier to entry if you want to play with something, and you're not going to have to go out and buy a $200 computer to do this. They are very different though. Raspberry Pi is a microcomputer. It runs Linux, and as of very recently, Windows 10. There are 5 different boards. And they're between $25 and $35 without accessories. I've got 3 different Raspberry Pi versions here today with me. Our Arduino is a microcontroller, and I'll go over in a minute what the differences are between a microcontroller and a microcomputer. There are countless different Arduino boards out there, and I'll get into why that is here in a minute as well. And they run anywhere $10 to $50. So what's the difference between a microcomputer and a microcontroller? A microcomputer is a full computer. It has CPU, it has memory, it has Ethernet, it has display ports, etc. A system like this, like the Pi, is called a single board computer. Everything about the computer is in one small little form factor on a single board. They have an operating system on it. You have to load Linux, you have to load Windows in order to get them to work. And you can program these things using any programming language that it supports. So if you load Windows 10 on here, Visual C++, C#, .NET, whatever you want to program with, you can load it on here and get it to run. For Linux, I'll be touching on a little bit of Python today, and Scratch is also very popular and is used on these a lot. Microcomputers have the ability to multitask, and that's a very big distinction between a microcomputer and a microcontroller. And some examples of them are Raspberry Pis, BeagleBones, etc. A microcontroller, on the other hand, is a single integrated circuit with CPU, memory, and then usually general purpose I/O pins. You program this chip directly. Almost every single microcontroller will have some sort of programming interface, an IDE, for you to deal with. But besides that, there is no operating system. There is no firmware. These chips usually run a single execution path. There is no multitasking that happens in these chips. Additionally, they can be very easily expanded with different other shields to add different capabilities, such as Ethernet, disk I/O like a micro SD card, etc. And there are several Arduino variants. Most of them use the Mega 328P chip, but then also you can buy ARM CPUs, which you can program directly as well. are interested in going that route. So let's look a little bit at the hardware between the Raspberry Pi 2 and the Arduino Uno. Raspberry Pi 2 is a quad-core 900 megahertz ARM processor. An Arduino is a 16 megahertz processor. The Raspberry Pi is 32-bit. The Arduino is 8-bit. RAM, 1 gig on the Raspberry Pi 2. You have a whopping 2 kilobytes on the Arduino. Flash, 32 kilobytes on the Arduino, and the Raspberry Pi can take whatever micro SD card you can throw at it. You have a couple of differences in the GPIO pins and how much power each will output. But take a look at the power. Oh, hello. Oh, something messed up. Okay.
Push that button.
The pie started flashing too.
Okay. The power difference. Raspberry Pi 2 can take upwards of 4 watts, whereas an Arduino, 175 milliwatts. That's a lot less. It makes the Arduino very capable to run off of a single AA battery, whereas a Raspberry Pi, you probably aren't going to be able to do that very effectively. As far as code availability is concerned, the Raspberry Pi does have some closed source code, but the Arduino is completely open source. The design of it is completely open source, and all of the parts can be bought individually off the shelf. This has led to a whole bunch of variants of Arduino existing, because anybody can build an entire board. So you'll find a lot of official boards, but you'll find a lot of unofficial boards as well. The one I have today is actually an unofficial board that I bought for about half the price of an official board. So I'll show you how it works. And then the operating system. You have Linux on the Pi. You don't have anything on the Arduino. It's just what you program. So some common usages. Raspberry Pis are good for multimedia projects, cameras, music, video. I use one at home to watch TV and watch all of my movies that I've encoded into MKV format. You know, that's what it's good for. It's good for processor-intensive applications and Internet of Things applications. Anything where you Google, upload sensor data to spreadsheets, Raspberry Pis are great at that. And the other thing that they could be used for is to control an Arduino. Pis and Arduinos have serial interfaces, and you can use them to control and read data back and forth between them. Arduinos are very good for sensors and more sensors. They're very good for driving motors and low battery applications. Just for you to have some idea here, I've got to pick this up. It's a 37 sensor kit for Arduino, and it was about 20 bucks. Lots of interesting things like flame sensors or touch sensors or heartbeat sensors. So lots of interesting things that you can do with that. You could also consider the Arduino to be slightly more secure. If you have an application that you're worried about somebody hacking into, with the Pi, you've got a full Linux stack. You have to worry about security patches. Whereas the Arduino, you load it, you program it, and that's it. It just runs it. It doesn't really have a lot of visibility or hackability at that point. So I want to cover a bit of basic lingo and do a small electronics primer, and then we'll get on to the fun stuff of the program. Some hardware lingo that I might use today. This is a breadboard. It is useful because it has, and I'm not going to use the laser pointer, a positive and a ground or negative side that goes up and down both sides. Those are all electrically connected in a big long line. And then each one of these rows is electrically connected going horizontally on the fretboard. A breakout cobbler. This allows me to take a ribbon cable and go from a Pi or an Arduino over to a breadboard so that I can more easily use a breadboard for electrics. An add-on shield. An add-on shield is pretty pretty much a plug-in module that you put on top of a Raspberry Pi or an Arduino. It usually makes it so that ports are more easily accessible or adds features like that one would add an Ethernet port and a micro SD card on it. A perma-proto shield. Similar to the shields, this allows you to do some more permanent electronics work by actually soldering wires and chips right to this shield, which would then make it a little bit more easy to use. We'll point around here.
Yay.
Now we got two remotes, wow. Jumper wires. You'll see lots of jumper wires when I get this going. There's usually three types, male to male, female to female, and female to male. Some basic electronics hardware, resistors. Resistors are very important, and we'll do an exercise here in a little bit. I was going to use my notes to actually say these. Resistors are passive electrical components that act to reduce current flow and lower voltage levels within a circuit. Fancy. Capacitors help smooth out voltages in a circuit. They're very good for providing momentary voltage in case you have a voltage spike in your electrical circuit. And an LED, a light emitting diode. Hopefully everybody knows what an LED is. Good. Right, so I want to go over a basic electric current with an LED. Let's figure out what we need to make a circuit to light up an LED. For this example, I'll be using a 3.3 volt power source and have an LED that will blow out with a current greater than 25 milliamps. Have you ever seen an LED just blow up? Yes. Yes. Yeah, it's very easy to do, and if you just wire it up and plug it in, most likely you're going to make it blow up. The LED will use some of the voltage in the current on the circuit. And what electrical laws do we need to deal with this circuit? There's two that I'm going to be talking about today. Kirchhoff's voltage law, which is the directed sum of electrical potential, or potential differences, otherwise known as the voltage, around any closed network is zero. Also known as, in an electrical circuit, the amount of voltage generated equals the amount of voltage used. So in the end, we have to have a big net zero of electrical energy in order to make this work. Using KVL in an LED circuit, let's figure out how we wire this up. We're going to use KVL. Our input voltage, as I had said, was 3.3 volts. An LED forward voltage, or its drop, what it's using, is 1.8 volts. So if we apply Kirchhoff's voltage law, we end up needing to still use up 1.5 volts in our equation. And we're going to do that by using a resistor. Which leads me to my second law that I want to talk about, and this is it, two laws. Ohm's law. The amount of current I in amperes equals the voltage V over resistance, R. So let's use a resistor to use up that remaining 1.5 volts in our circuit. LEDs have suggested currents that they suggest that you use in order to get the best life out of them. In this case, our LED suggested current is 10 milliamps. Doing a little rearranging of our equation, we get voltage equals current times resistance. And we have 1.5 volts equals 10 milliamps, which is 0.010 amps, times resistance. Solve for R, and you get 1,500 ohms, or 1.5 kilo ohms. So when we make our system, or when we make our circuit, we'll use a 1.5 kilo ohm resistor. And when that happens, everything will work, and we won't blow out our LED. And I'll show you an example of it. Okay, this is hard to see. If you look way over here in the corner, you'll notice this light, nice, lovely, blinking LED. Right next to it, this piece right here is a 1.5 kilo ohm resistor. which is hooked into our 3.3-volt circuit. So if I take that out, I'll probably fry it. You want me to fry it?
Do it.
Let's see if I can fry my LED. Oh, yeah, okay, so you saw it light up briefly and then go up. So it is now a dead, oh, no. Sorry about that. Okay, so this was a better one than I thought. Sweet.
You need more power.
Yeah, maybe that power supply is weak too, that would be possible. So from our previous example, we figured out, oops, hello. Let's play around with our equation a little bit more here. What's the brightest LED I could possibly make without blowing it out? If our LED's maximum current is 25 milliamps. Do the math, we would end up with a resistance of 60 ohms. That 60 ohm resistor would give us quite possibly the brightest LED that we could without it blowing up on us. And it seems to be working fine without one even. So 60 ohm resistors aren't standard, so we would use our next standard resistor value, which is 62 ohms. From our previous examples, we figured out two different resistor values and the suggested current for the LED and the maximum current. Now, let's see who is paying any attention here. If I have those 4 resistors, who can rank them in the order from brightest to dimmest?
100, 360, 1 kiloohm, and 15.
Very good. Well done. So, all right. Okay. Done with the math. Done with the learning piece. Let's go into the Pi a little bit more here. This is a Raspberry Pi Model 2. It's pretty new. It came out, what, 6 months ago, a year ago, something like that. 900 megahertz quad-core ARM7 CPU, Gig RAM, hardware decode, or encode and decode engine in the GPU. A nice little board to play with. When you play around with programming, you need to know the pins and what your general purpose I/O pins actually do. This is a nice breakout of the different pins and all the different things that are used. I don't know, anybody familiar with I2C at all, or SPI? Okay. There are different ways to pass messages, and it allows you to string a whole bunch of components together on one common bus versus individually wiring them all to individual general purpose I/O pins. Moving on, Raspberry Pi Model A+. This is an older model. It also is a lot smaller. Notice that it only has one USB port, and it's about half the size of the other Raspberry Pi models. The B+ looks very similar to the Raspberry Pi 2, with the exception that it's got less RAM and an older CPU as well. So where do you go to learn more about Raspberry Pi? I suggest Adafruit. Adafruit, if you've ever been to this company's website, is a shop and learning portal with lots of information on Raspberry Pi and other microcontrollers. A lot of the stuff in the examples and the demos, which I'm going to do shortly, come from the Learn site here at Adafruit. So they will walk you through everything from setting it up to doing configuration to driving motors, etc. Okay, now we get into some programming examples. Adafruit provides a very nice Python library called the Python GPIO library. And it makes interfacing with GPIO pins very easy. In this case, if we want to turn on an LED on pin 18, we'd use the following code. We import the GPIO module, we set our pin number, We do a set mode command, which is something that's specific for this GPIO library and the Pi's. Set it up as an output pin, and then turn it on. Set it to 1 or true. And that simple code will make that LED turn on. Turn it off, you set it to a 0 again. Very easy. It's not complex at all. Inputs is very similar. You set our mode, you set it to an input mode, and then you read in the state. If the state is true, that means you have active current going through it. Or if it's false, like here, it would indicate that, for example, I had a push button that I pushed in order to break the circuit, to break the flow of electricity. Very simple when you just look at the very basics of it. Scratch is a very popular programming language which has native support in the Raspberry Pi as well. However, it doesn't support GPIO out of the box. It is very nice if you're just looking for a Scratch platform to program on. But there is a helper program that can be used to interface Scratch with GPIO pins. The project is called Scratch GPIO. And it does something like this. Basically, you have a helper program that runs in the background, which is a set of Python scripts which interface with Scratch and allows you to do the various pin 11 on, pin 12 high commands that would exist in the Scratch programming language. I didn't take the time to figure out a live example for this, so I just want to mention this here in case you're a good Scratch programmer. Like to use Scratch. So let's move now into Arduino. This is the Arduino Uno version 3. It is an Atmega 328P CPU. I have 14 digital and 6 analog general purpose I/O pins, 32K of flash and a whopping 2K of RAM, and it runs at 16 megahertz. Here's your pinout, in case you're interested. It's really hard to read. Unfortunately, it's well labeled on the board, so you really don't need it all that much. This is the Nano version 3. It's identical specs to the Uno version 3, just in a very different form factor. This Nano is designed to plug directly into a breadboard or a protoboard. It has a USB 2 mini connection instead of a full-size one, and it's only 3/4 of an inch by 1.7 inches, so very small. And I have one of these. I have both of those up here if you want to look at them in person. The Mega. This particular Arduino has a bigger processor on it so that it can support a whopping 54 general purpose I/O pins. You're still limited with 32K flash and 2K of RAM, but a whopping 4 inches by 2.1 inches. If you can get 54 sensors on this, I'd be very impressed. I want to see it done. Programming in Arduino is done through the Arduino IDE. Coding is done in C. Well, it's very C-like. I can't find for certain whether it's pure C, but it's very C-like.
It's C++.
Is it C++? Is it pure?
Not pure.
Not pure. Codes for Arduinos are set up in 2 parts. You have a setup and initialization section, and you have a repeating infinite loop. You compile the code on the IDE and then upload it to the Arduino via the USB interface. And I'll do some examples of this in just a minute. For example, this code here, we're going to do our same LED routine that we did with the Pi. We're first going to set in our setup function, initialize the pin as an output pin. And then in our repeating loop, we're going to turn it high, which turns it on. Wait a second, turn it low, which turns it off. And wait a second. And this loop will run for infinite. It'll run until it loses power, or it'll run until you reset the power on the Arduino. And anytime it's disconnected from the computer, once the Arduino has its program, it executes it. That's what it does. So when you have your code, you compile it and upload it in the IDE to the Arduino via USB, and it'll reset and start executing. So, live demos. First of all, I just want to show you guys a little bit of what I brought with today. You can't see that. Okay. Hey, that's more interesting. Okay, so with me today, I brought along a couple of Raspberry Pis and 2 Arduinos. This is the 2, if you just want to look at one. I'm not going to actually run anything on there. I have an A+, plus a camera here. And if you noticed, if you happened to walk by my office yesterday, you may have gotten captured on camera. And I got my first victim that walked by was Brian. And there he goes. Oh, you can't see that. All right. My first victim was Brian.
Very angry. Oh, right, true. Oh, what was I thinking?
All right,
Yeah.
so since I'm here, I'm going to just do. Okay, everybody can see this, right? Yep. All right. I'm going to show you some basic code that I've set up here. This device here is a Raspberry Pi that's hooked into a couple of breadboards and via a whole bunch of jumper wires. It additionally has a temperature humidity sensor on it, which is the blue thing here, to sense the temperature and humidity. So I'm going to show you a little bit of code, because we're programmers, we like to see code. And then I'll show you how it works. So this is a Adafruit example code, and there's a ton of comments in it, but it's fairly easy to use. You have to set your sensor and your pin numbers, but besides that, you have one nice command that actually does the reading of your sensor data. So this makes it very easy for you to get your sensor data, and once you have it, you could do things like, I don't know, put it in a spreadsheet and graph it, or say if one of the common uses for something like this, for some people that I know, are they like to brew their own beer. So they put this in a freezer, and if the freezer gets too warm or too cold, it'll either turn on the freezer or turn off the freezer in order to keep it at the right temperature. So lots of different things you can do with this. And let me show you how, just let it run here. And you get an output of, right now it thinks it's about 71.6 degrees and 34% humidity in here. Similarly, I have this nice LCD screen on this board. It's a 16 character by 2 character LCD screen for outputting whatever you want. For this particular code, we have a lot more pins to set up at the top. And then we have our nice loop that we go through here. So I get the humidity and temperature the same way that I did before. As long as everything checks out with that, I can very easily print to the LCD using one line. So this is how, it's not complicated how to do this. It's very simple and it's very accessible for even learning programmers. I don't know how many of you here have even taken the Python intro class, but I don't know Python very much at all, but I can figure out enough to get going here. And let me show you how that runs. So this particular one, this particular Python script is set to go between the time temp and the current IP address that I have on wireless on Arduino. So I can figure out how to log into this thing if I need to. In addition, this script also lights up my the LED up here when it's querying the temperature sensor, which you should see right there. So pretty easy stuff to do. And one last one that I wanted to do. Certain pins on both the Raspberry Pis and Arduinos are set up as pulse width modulation pins. Have you ever heard of that before? PWM. Basically, it allows it to not send a full current 100% of the time, but it'll send a percentage of that current. So if you, for example, want to send 25% of that current, it'll do a cycle, it'll cycle the power on and off very rapidly so that about 25% of the current gets through the circuit. This is very good for things like controlling motors. If you want motors to go faster or slower, the more current you send, the faster it's going to go. I'm showing you how it works here with an LED. If you can see how the brightness of that is flickering, I just have a random flicker program going on here to do that. All right, any questions on the Raspberry Pis before I move over to the Arduinos? No? Okay, Arduinos, as I said, are programmed it's a language very similar to C++. It's not 100%, but it's very close. This is the Arduino IDE that you program and then upload your code in. This is the example link program. I don't know if you can, I can't really hold that up at the same time. But you've got two parts. You do your setup, which is your run once at the beginning, and then you have your infinite loop, which runs repeatedly until the Arduino turns off. In this case, I am setting pins 13 and 12 to high voltage, which turns them on, and after a second, it turns them off by setting it to low voltage. Let me show you a more interesting. If you happen to walk by my office, oops, if you happen to walk by my office earlier this week, you may have heard me testing a sensor that I've hooked up here. This is a motion sensor. This little sensor right here detects, or should detect, a warm-blooded motion. And I've set this up to both output via the serial console, and this is going to keep going on me. Let's go over the code a little bit. I've got some initial setup here, where you start your serial, you start your inputs and your outputs, and away you go. The main loop is here. The basic gist of this code is that if you are getting an output from this particular sensor, you are in a high state, and as soon as it goes away, it should go into a low state, and I think I have a crossed wire somewhere because it's beeping when it shouldn't. But in order to upload this to the unit, you need to compile it, which I'll show you how to do. Verifying and compiling it. Compile, and then uploading it, then uploads it over the USB interface, and then resets the device. Watching the serial monitor, you can see that it's calibrating or attempting to calibrate the sensor, and when it's done, we now enter into our motion phases. So let me show you a few other of the fun sensors that we have. In celebration of the Star Wars trailer that was released yesterday.
Oh.
You can get it to play music via a speaker. And this one I couldn't figure out on my own, so I did have to look this one up. So, but your code is basically this: a whole bunch of beeps with different tones. And now this Arduino is now programmed to run this ad infinitum. So disconnect it, and you can just have it play as forever if you want. Which I don't. This device here is a small distance sensor. It will detect distances up to 100 centimeters. Well, it should accurately do. So this one I've set up to, along with detecting approximately how many centimeters away my hand is, it plays a pitch that changes with the, and if that's actually 500 centimeters, I'm impressed. It's only supposed to work up to about 100, so. But this could be used for like motion detection. If you want to create a robot and you want to make sure it doesn't crash into a wall, you put one of these on the front of it, and when it gets within 10 centimeters, you make sure that robot stops. Would be an excellent use of this particular sensor. Let me go back to. Before I do that. Yeah, sure.
Are there good availability of like really high-end versions of these sensors? Or
Yes, they're pricey. Yeah. Again, as I mentioned, this was a 37 sensor kit, and I picked it up for $20. Some of the high-end version of these sensors you can get $60–70 just for a sensor. So, but now the accuracy is huge on those, but you get what you pay for. I'm a hobbyist. I like to just experiment with this stuff.
Accelerometer.
I do have one, but I don't have any code for one right now. An accelerometer would be a sensor that picks up how many G's you're going and in what direction you're going. So you can have 3 different axes that it'll pick up how many G's are going. So X, Y, and then Z. You'll find these in like a drone would be a good example. It would be a good use for an accelerometer. Usually those also come with compass modules built into them, so you can get a compass reading. And some of them actually will do basic GPS, where it figures out how far from magnetic north you are as well. So some very interesting ones.
Can you get an interface for HomeKit so you can have it turning on and off the lights in your house time of music or something?
If you can think it up, you can probably do it.
So,
Like being ignored.
I'm going to show you the, if you can see it on here, I have a second Arduino right here, the Arduino Nano. It is hooked up to this is an RF module. It's a 2.4 gigahertz RF module. And I'm going to take, I have a paired one attached to this proto shield, which I will install and then see if I can get them both running together and talking back and forth between each other. Give me 1 second to get this going on. Okay, so I've got two RF modules here. The Nano, I've already uploaded ahead of time with the code to, if it receives a signal, it should bounce it back with its current time so that we can figure how long it took for it to send the signal between the two devices. And now we'll see if they can talk to each other. Hey, they do. Awesome. Okay, so this is a very, this is the serial interface of the big Arduino here. And it is sending out a packet along with its time, and then it gets a response back, and then figures out the delay. So 1800 microseconds is a very short delay. If one of these lost power, you would see that it's now failing. And then plug it back in, and after a few seconds, it should pick back up and start responding again. There you go. So, these RF modules work at approximately 20 megabits per second. So they're very, they'd be very good for short distances, sending even like a live video feed between two devices. So lots of different options. What do I want to do with this? I got into this because I like to play and tinker. What I want to do is set up a RC car that has a camera on it that I can control with my phone. That's what I really want. Another thing that I would really like to do as well is take a GPS module on an RC car, drive around the block, and then say play, and have it self-drive itself using GPS. And that's all easy to do, as long as you can put the time in for the programming and buy the sensors. So. Everything you see here that I've brought with today is probably about, maybe about $150 after buying all the Arduinos, all the Pis, and all the sensors. So I've invested into it over a little bit of time here, but it's a lot of fun. And that's my hobby, so that's what I have for you today. So thank you.